Hello, welcome to the video of session 9 of module 2 fast Fourier transform algorithm of the subject digital signal processing, which is prescribed for 5th semester electronics and communication engineering students. First, let us have the learning objectives of this session. So in this session, first we will be considering finding inverse DFT using radix2 FFT algorithms. Then we will be considering converting DIF-FFT algorithm for computing DFT to DIT-FFT algorithm for computing IDFT. Then we will be considering some of the examples, that is illustrative examples using DIT-FFT algorithm for IDFT computation. First, let us have inverse DFT using radix2 FFT algorithm. DIT FFT algorithm for IDFT computation, there are two methods for calculating IDFT. One is using DIT FFT and another using DIF FFT algorithm. These two algorithms are similar to that of finding DFT using radix2 FFT algorithms. As introduced by Cooley and Turkey, first what we're going to do is, as the number of samples in the incoming samples or incoming sequence, that is capital N, if it is a composite number, then what we will be doing is we are dividing or we are splitting till we obtain 2-point TFTs. That technique comes under divide and conquer approach, that is introduced by Cooley and Turkey. And in that divide and conquer approach, there are three subcategories, that is radix2 FFT algorithm, radix4 FFT algorithm, and split and radix algorithm. In that we will be considering radix2 FFT algorithm. In radix2 FFT algorithm, there are two kinds of FFT algorithms. One is decimation in time FFT algorithm, and one more is decimation in frequency FFT algorithm. So what we considered is, for computing discrete Fourier transforms, we were employing these two techniques, that is DIT FFT algorithm and DIF FFT algorithm. Okay, what we are doing is, as the equation for DFT and equation for finding IDFT are similar in many cases, except few changes, we can employ the algorithms available for computing DFT to compute IDFT also. So, how to do, we can see in this particular session. First, let us take DIT FFT algorithm for IDFT computation. So, this is decimation in time fast Fourier transform algorithm for inverse discrete Fourier transform computation. So, what we know? We know the equation for finding IDFT. That is, IDFT is nothing but reconstruction of time domain samples from the frequency domain samples. So, as we know, this x of k is a DFT, that is frequency domain signal, which we obtain by taking DFT on x of n. But what exactly we are doing here is, we are retrieving or reconstructing the time domain sequence from this frequency domain samples. Okay, so IDFT is given by x of n is equal to 1 by n, summation k varying from 0 to n minus 1, x of k into wn raised to power of minus kn. Here the value of n is varying from 0 to n minus 1, and this wn is nothing but our twiddle factor. But observe the equation for DFT. Here this x of k is representing n point DFT of x of n, which is given by x of k is equal to summation n varying from 0 to n minus 1, x of n into wn raised to power of kn, where the value of k is varying from 0 to n minus 1. So, from these two equations, what we can say is, this is representing the frequency domain sampling, and this is representing the reconstruction of time domain samples. Okay, so both x of n as well as x of k are n samples, that is capital N number of sample sequence. Now let us have the difference between DFT and IDFT equation. As we saw in the previous slide, here x of n as well as x of k. If we carefully observe the differences, see, first difference what we obtain is the factor 1 by n. So this factor 1 by 1 n we can see in equation for IDFT, that is absent in case of equation for DFT. And the other main difference is sign of the power of twiddle factor. So in case of DFT equation, the sign of the power of twiddle factor is positive. If you come for the IDFT equation, sign of the power of twiddle factor is negative. So with these changes, we can convert DFT equation, methods to find DFT to methods to find IDFT. So therefore, our FFT algorithm for computing the DFT can be converted to FFT algorithm for computing IDFT also. So the steps for converting the decimation in frequency fast Fourier transforms algorithm for computing DFT to decimation in time FFT algorithm for computing IDFT are, we will going to consider this one by one. So first what we need to do is we have to first take the flow graph of DIF FFT algorithm, which is for finding DFT. Okay, so in that flow graph, first we have to reverse the direction. That means in case of finding in computing DFT, in case of DIF FFT algorithm, first we were taking x of n as input and we were obtaining x of k as output. But here we are reversing the direction. So obviously our input will be x of k and output obviously will be x of n. So next step is we have to change the sign of power of twiddle factor, WA. So in case of DFT, for finding DFT in DIF F50 algorithm, the sign of the power of twiddle factor were positive, but here we have to change it to negative. Then what we need to do is we have to replace our x of n by x of k as well as x of k by x of n. Next, at the end of the flow graph, we have to multiply the output by the factor 1 by n, because in case of equation, if we consider the equation for finding DFT, the factor 1 by n is absent. But if you consider the equation for IDFT, the factor 1 by n is multiplied with the summation n varying from 0 to n minus 1 x of k into Wn raised power of minus k. So this 1 by n we have to multiply at the end of the flow graph. Now let's have the flow graph for DIT FFT algorithm for finding IDFT computation for endpoint. So this is the DIT FFT algorithm for the IDFT computation. How to obtain this is this represents the flow graph for finding IDFT using DIT-FFT algorithm. This is for the value of n is equal to 8. So you can observe here, first we will be giving the inputs, that x of k in natural order. So this is in normal order and the output of the first stage will be taken as input to the second stage. Then output of second stage is taken as input to the third stage. So after the last stage, we will be multiplying all the values or all the samples with the factor 1 by n. Here the value of n is 8. So it is, we are multiplying by 1 by 8. So here we are obtaining our output, that is x of n in bit reversal order. So x of 0, x of 4, x of 2, x of 6, x of 1, x of 5, x of 3 and x of 7. So now To understand this concept in better way, let's have some of the illustrative examples. So first example we are taking as the value of x of k is given as 4, 1 minus j 2.414, 0, 1 minus j 0.410, 0, 1 plus j 0.414, 0, 1 plus j 2.414, and we need to find x of n using DITFFT algorithm. So now let's have the solution for this. So they have given 8-point DFT. We need to find the corresponding 8-point IDFT. So x of k, what they have given is 4, 1 minus j 2.414, 0, 1 minus j 0.414, 0, 1 plus j 0.414, 0, 1 plus j 2.414. So we require 4 twiddle factors, that is twiddle factor the W8 raised power of minus 0, W8 bar minus 1, W8 bar minus 2 and W8 bar minus 3. So W8 bar minus 0 is 1, W8 bar minus 1 is 0.707 plus J 0.707, W8 bar minus 2 is plus J. Similarly, W8 bar minus 3 is minus 0.707 plus J 0.707. So now this represents the complete flow graph along with the complete answer with step by step. We can observe here, we are considering the input in normal order. Observe, x of 0 is equal to 4, x of 1 is equal to 1 minus j 2.414, x of 2 is equal to 0, x of 3 is equal to 1 minus j 0.414, x of 4 is equal to 0, x of 5 is equal to 1 plus j 0.414, x of 6 is equal to 0, x of 7 is equal to 1 plus j 2.414. After performing the first stage of computation, sorry, we obtain the output from this first stage is as 4, 2 minus j2, 0, 2 plus j2, 4, minus j 2.828, 0 and minus j 2.828. So these are taken as input to the next stage. So output from this second stage of decimation are 4, 4, 4 and minus j4. Similarly, here the outputs are 4, 4, 4 and minus j4. And now we will be considering these outputs along with the twiddle factors here. So that values will be taken as inputs to this particular stage. So we will be obtaining inputs. We are giving inputs as 4, 4, 4, 4, 4, 4, 4. So output from this will be multiplied by the factor 1 by 8. So after multiplying 1 by 8 with this, what we obtain at the end is x of 0 is equal to 1, x of 4 is equal to 0, x of 2 is equal to 1, x of 6 is equal to 0, x of 1 is equal to 1, x of 5 is equal to 0, x of 3 is equal to 1 and x of 7 is equal to 0. So our output x of n is 1, 1, 1, 1, 0, 0, 0 and 0. 4 ones followed by 4 zeros. That is the required output. So now let us take the next example. X of k is equal to 0, 2.8284 minus j 2.8284, 0, 0, 0, 0, 0, 2.8284 minus j 2.8284, and we have to find x of n using DITFFT algorithm. So now let us solve this. Again here the value of n is 8 and we have to find the twiddle factor W8 power minus 0, W8 power minus 1, W8 power minus 2 and W8 power minus 3. So given value of x of k is 4, 1 minus j 2. So given x of k is 0, 2.8284 minus j 2.8284, 0, 0, 0, 0, 0, 2.8284 minus j 2.8284. The twiddle factors W8 power minus 0 is 1, W8 power minus 1 is 0.707 plus j 0.707, W8 power minus 2 is j, W8 power minus 3 is minus 0.707 plus j 0.707. Okay, so this is the answer. So here x of 0 is 0 because we are taking this inputs in natural order. X of 1 is 2.8284 minus j 2.8284. X of 2 is 0. X of 3 is 0. X of 4 is 0. X of 5 is 0. X of 6 is 0. X of 7 is 2.8284 plus j 2.8284. Okay. After first stage of decimation and after multiplying with the twiddle factors, we obtain the outputs from the first stage as 0, 2.8284 minus j 2.8284, 0, 2.8284 plus j 2.8284, 0, 4, 0 and 4. So this output from the first stage now we will be considering as input to the second stage. And after performing the calculation and after multiplication with this twiddle factors, we obtain the outputs of the second stage as 0, 5.6568, 0, 5.6568, 0, 8, 0 and 0. Now, we will be considering this as input to the last stage. So, we consider that afterwards what we will be doing is we are multiplying with W8 power minus 0. So, that obviously will be multiplied with 1 is same thing we will be getting. But at the end of this flow graph, we are multiplying all the samples with 1 by 8. That is the factor 1 by n. So, we obtain x of 0 as 0.707, x of 4 as minus 0.707, x of 2 as 0.707, x of 6 as minus 0.707, x of 1 as 1, x of 5 as minus 1, x of 3 is 0, x of 7 is 0. So our output, that is IDFT, x of n is given by 0.707, 1, 0.707, 0, minus 0.707, minus 1, minus 0.707 and 0. That is the answer for this particular example. So, what we learned from this particular session are, we first look into how to find inverse IDFT using radix to FFT algorithm. Then we took up how to convert the DITF FFT algorithm for computing DFT to DIT FFT algorithm for computing IDFT. Then we considered some of the illustrative examples for finding DIT FFT algorithm for IDFT computation. So, with this, we will be concluding this session. The references we considered here are book written by Prokis and Monolokis in their book Digital Signal Processing Principles, Algorithms and Applications. And the second book we referred is book written by Li Tan and Jin Jiang in their book Digital Signal Processing Fundamentals and Applications. And another book we referred is the book written by Mr. Uday Kumar S. in his textbook Digital Signal Processing. And for the contents of this particular session, you can access through these given links. So with this, you can have the access to the 7th session video link, and with this link you can access to the corresponding session PPT, and with this you can access to the multiple choice questions of this particular session. And this, from this you can download, or you can check, or you can view the notes of this session 4, sorry, session 7 of module 2. And this is our LMS team which is responsible for this particular video session. Thank you. Thank you.